Hey guys, last week I made note that you should go through a couple of things in the notes in this unit just before we move into concentration. And those things were properties of gases and their solubility, polar and nonpolar substances, and then properties of solutions themselves. Now, these things aren't overly complicated, and so that's why I gave it more as an independent thing for you to do. But I'm going to go just through some of the finer points and some of the more important things in this video, just so that you kind of have a better understanding of some of the more important things. So first things first was the solubility of gases. So as you probably know, generally speaking, when you heat things up, say like water, you can usually dissolve more stuff in it. So sugar, salt, and things like that, you can usually dissolve more at a higher temperature than you can at a lower temperature. However, gases tend to be the opposite. They will decrease in solubility when the temperature goes up. So you might actually see a couple of these lines on here, like this guy and this guy, they're showing that trend here. And if you look, these ones, they are indeed gases. Now, it's not necessarily all of the ones that are going down that are gases, like for example HCl there, but generally speaking, gases are going to decrease in solubility when the temperature goes up. And the reason for that is, if you remember, going back to gases themselves, they are already high energy particles. Okay, they are already moving super fast as is, and so usually if you add more energy to something that's moving already very quickly, they're going to speed up even more. And that means it's going to be very difficult for the solvent particles to keep them dissolved inside of that solution. And so when you heat something up like a gas that's already moving quickly, it becomes less soluble. So in these cases, decreasing temperature will actually make the gases more soluble. Okay? Because again, think of it this way, the particles are now slowing down, and so they can't really get away from the solvent particles. They're now going to be trapped inside because they are moving more slowly, and then the solvent particles now can surround them, because remember, for something to dissolve, the solvent has to surround it, the solute particle. And so now that they're slower, they're a little bit easier to catch. They have less energy, so they are a bit easier to hang on to, and they can't overcome the intermolecular force. Okay? And so yeah, that's all there as well. So the thing is, when you add the energy too, they can break free of the bonds that are holding them back. So remember, particles have that intermolecular force that kind of keeps them in place. And so if you add an energy, it makes it easier for them to break away from that. So another thing that affects the solubility of gases is pressure. Okay, pressure again is the force that's kind of squeezing down on them, preventing them from moving. So the more pressure that is exerted on a solution, the more gas that can be dissolved. Because again, gases like to move around. They like that freedom. They move around very, very quickly. And so by compressing them more, they're losing that ability. And so now they can no longer really get away from the solvent particles, and they kind of get forced into it in a sense. Possibly against their will, but such is life. So some examples are actually just a little bit more on that. Like I said, these particles are being forced into the solution. So if you look at this little diagram here, oops, okay, no pressure, or not a lot of pressure has been exerted on there. And so the gas molecules up here, they're kind of happy floating around in the empty space. They got more room to move around. There's no real reason for them to go into the liquid portion down here. And they're just kind of being happy gas particles floating around. Okay, but in the next one on the side here, okay, the thing has gone down, and so we've increased the pressure, and now we're kind of compressing the space that they originally had, and they don't really want to be too close to each other. Again, they want that freedom to move around, and so they're going to try and go into the solution to get away from some of the other gas particles in that airspace. And now they get forced into it in a sense because they realistically have nowhere else to go at this point. Okay, they're pressed down in. Okay? So by restricting their movements even more, again, those solvent particles, they have a better chance of grasping them and hanging on and keeping them inside the solvent. Okay, and overcomes their force of their forces of when they're moving to get away from them. So an example, something you probably know and love, a carbonated beverage, whether it be bubbly, Coke, Sprite, anything like that, there's obviously a large amount of gas inside. Okay, those beverages, they have to be bottled or canned or whatever thing they're in a sealed and under high amounts of pressure. Okay, the high amounts of pressure again forces that into the liquid, and so that carbon dioxide, which is making those bubbles, gets dissolved in the liquid. And that's actually why too that when you open up a seal on, say, a bottle or a can, you hear that sound, because that pressure is now released, and so all of that gas is now free to come out. Before you actually open, you can see it better obviously on a bottle than on a can, but before you actually open that for the very first time, it's difficult to see the individual bubbles. Once you twist the cap off and release that pressure, you'll start noticing the bubbles starting to rise out and coming out of the solution. Similarly, if you were to leave that bottle just standing in your room open, eventually overnight, for example, if you go back to drink that, not only will it be warm and less delicious, but it may have lost some of that fizz, because overnight more and more of that gas came out of the solution because they don't want to be trapped inside that. And the other thing too that's important is that your room typically is warmer than the fridge, and so not only are the gas, have they lost the pressure that's keeping them forced inside solution, but they're also gaining kinetic energy due to the fact that the temperature is higher than in the fridge, and so they're moving around more, and so that fizz is now lost. Okay, that's also why it's important to put the drink back in the fridge once you are done with it. So that just kind of slows down that process of the gas escaping and keeps it with that nice fizz for a while longer. Another example of gases being stored under pressure is in scuba diving. So the scuba tanks themselves contain pressurized air. Okay? Tanks in scuba diving can range between 40 to 80 liters. When you really do think about that isn't a whole lot. I mean, for those of you in biology, you may or may not remember that the maximum lung capacity for air on your biggest inhale as you possibly can is anywhere between 5 to 6 liters. So assuming you had a 40-liter canister, that's maybe 8 deep inhales. And if you're swimming, using up a lot of energy and a lot of oxygen, that's really not that much. The reality is, though, is that there is a lot of air that's been put in there under a high amount of pressure. It's been forced in there so that you can last underwater for a long time. Okay, and actually, if any, not sure if any have ever gone before, but this thing here is actually a pressure gauge. So the pressure gauge tells you how much air you have remaining in your tank, and it's based upon the amount of pressure left inside that tank, not actually about the volume left. You would think, because you're taking in a certain volume of air each single time, that it might read that, and so you have a sense of how much you have left, but they actually measure it in pressure. Because the thing is that when you are scuba diving, the deeper down you go, the more pressure there is exerted on your body. Okay, so if you were just 10 feet down, that's not that much pressure on you, and you can maybe go down for a longer period of time, 45, 60 minutes, okay, depending on how efficient you are as a swimmer. But if you're to go much deeper down, that means there's more pressure on you, on your body. And the thing with that is the inside of you, inside, say, your chest cavity or abdominal cavity, there's empty space. And the water normally would crush that if you didn't have any air inside you. And so, to counteract that, you have to breathe in a higher pressure of air to keep the air inside you, preventing you from being squished. Okay? And so that's why, realistically, in terms of deep sea research, there's a limit to how deep you can go and for how long you can go, because the vehicles can only go down for so long. And the more air there is, the more likely it is to get crushed, which is problematic. So you breathe in pressurized air, and that will continually go down as you take in more breath. More pressure is released, and so there's less pressure available to you, meaning it's time to go back up. Okay? So that air, which is pressurized inside there, counteracts the pressure from the water. Okay? the thing is, as some of you may have seen in movies or so, is when you do float back up to the surface, you do have to do that a little bit more carefully because the pressure on your body is now being released. However, you were just breathing in concentrated, very, very highly pressurized air. Okay? And so normally under deep amounts of pressure, that just gets dissolved in your blood the way it's being dissolved in the water, and that's not a big deal. The problem is once that pressure is released, just like with the pop can or the soda, is that gas now wants to come out of your blood, which is the solution at this point. And so that there runs the risk of an air bubble forming in your blood if you do rise out too quickly, which again you may have seen in certain movies. And this it ranges in the effects. I mean, you've probably seen the ones where people hallucinate, and technically, in rare instances, if it's in the brain, yeah, it could. But there's a lot of other more serious issues that, well, not that that's not bad. There are a lot of other serious issues that can come up with a blood bubble, a a bubble forming in your blood, because that could block off an important artery, and then we have all kinds of problems from there. So that's why they say that divers should be ascending more slowly so that the pressure is released gradually and you can breathe out that high pressurized air before it has a chance to come out of your blood solution. So, if you ever do plan on going one day, take it seriously. It's not a joke. I mean, it is really fun. It's a really super neat experience, but get proper training before you do so, because you do have it is a riskier activity you have to be careful of. Okay? So the next topic that you were supposed to get through was the idea of polar and non-polar substances. So in terms of that, if you remember back to the very start of the unit when we talked about electronegativity, there were polar covalent bonds, non-polar covalent bonds, and then ionic bonds. Okay, and an ionic bond occurs when there is a large separation in terms of electronegativity. There's a big difference, I should say, and so there's a separation of charge. A polar covalent happens between two nonmetals where their electronegativity is still big enough that one atom in the pairing has a bit of a stronger pull. They're stronger in terms of their electronegativity, and so they pull the electrons more towards them, and they get that slight negative charge, while the one that's a little bit weaker loses a bit, isn't quite pulling as strongly, and so it's slightly more positive. A non-polar covalent bond happens when they're relatively equal in their electronegativities, and so they're pulling back and forth relatively equally, and no one's really gaining any ground, and so there's no actual overall charge with that. That being said, we come to 4 different types of solutions. The first one is that when you have a polar solvent and a polar solute. So in both cases, they have a separation of charge. Okay? So the solvent is going to dissolve a polar solute, no problem. Okay? If the solvent is polar, it has a separation of charge. You have the separation of the partial negatives like we do in water and partial positives, and they're going to pull at the negative and positive ions in that solute, or slightly polar ones, and they'll dissolve quite easily together. Okay? The second one is a polar solvent and a non-polar solute. So in these instances, the polar solvent won't actually be able to dissolve the non-polar solute in a lot of cases. There are rare instances where it can still happen, but for the most part, non-polar things don't like polar things. Okay, they want to stick to their own kind. Same with polar things. They want to stick to other things that have that separation of charge. They want to interact more so with them because they're attracted to those opposite charges. When something has a slight negative charge, it's going to be attracted to things that are positive. If things have a positive charge, they're going to be attracted to things that are negative. Non-polars are not charged at all. They're pretty equal, and so there's no real charge to them. And so the polar things are like, well, you have nothing that interests me, and I don't want to interact with you. Non-polars, on the other hand, they're going to say the same thing about the polar people. You don't really have anything that we like. We're going to stick with our own kind. You go over there. We'll do our own thing. We'll clump together, but just leave us alone. Okay? an example of this is water and oil. Oil is a non-polar substance, okay? And so if you were to pour oil inside of water, you'll notice that the oil itself actually is going to stay separate. You may form a layer depending on what you're pouring them into. So if you pour it in a test tube, you'll see a distinct layer forming. But even if you're ever doing it while cooking and you pour a bit of oil into a pot of water, that oil tends to form a big bubble at the top, and or a sphere, and they just stay together. You can eventually whisk it to kind of force it, but for the most part, you'll just end up with smaller bubbles all over the place, and they'll kind of congregate together eventually if you leave them. Okay, you don't really get dissolving happening. Same is true if you have a non-polar solvent with a polar solute. Again, same idea. They don't like each other. They don't want to be together. They have two different things. They offer nothing that the other wants, and so you don't usually see dissolving happening. Possible, yes, it can happen, but it's unlikely. But getting into that is beyond grade 11. So just know that, generally speaking, if they are not the same type, they won't dissolve each other. The last type is non-polar solvent and a non-polar solute. So again, in this case, they will interact. They do like each other. They don't have the separation of charge like you would see in a polar substance, and so they're cool to interact with each other, and they'll be okay with that. Okay. Again, the reason behind that is it's a little difficult to explain at this level without getting into some of the fancy chemistry. Part of it is with things tend to prefer to be more randomly organized than forced into a strict layer of organization. And so when there's an opportunity to be more random or spontaneous, or when there's more disorder, molecules actually prefer that, which is into something that's a little more complicated, thermodynamics and entropy. You'll get to that if you do any chemistry in grade 12 or further on down the road, and you'll see that happening. But overall, big rule of thumb here is like dissolves like. So non-polar things can easily dissolve other non-polar things. Polar substances can dissolve polar solutes. Okay? So if they are of the same matching type, solvation or dissolving is likely to occur. Okay? So polar molecules like to hang out with other molecules that are also polar, while non-polar ones, they like to hang out with other molecules that are like them and non-polar. Kind of like people. You like hanging out with people that are like you, and people that are not like you may not always hang out with. Okay? What tends to happen, though, if you do try and force them together, they have a tendency of repelling each other. Again, like with people of different personalities, you can put them all in the same room, but they may not always interact with each other. They may just go find people that are kind of similar to them and hang out with them. So molecules are just like that too. Okay. The last little bit here was on solution properties. But so essentially what happens is that when you dissolve something inside of a solvent, the original properties of the solvent get altered in some way. Okay. So if a pure substance, say water for example, will have different properties from that of salt water because we have salt dissolved in it, which realistically kind of makes sense. Pure water is not the same as salt water. You wouldn't use them for the same two things. They don't behave the same. So, realistically, you have water plus something else in it. So it makes sense. Okay. So some things that you will notice is that boiling point gets elevated. So it boils at a higher temperature. So example, salt water, it boils at a slightly higher temperature. Water typically should boil at about 100 degrees Celsius. If you add some salt to it, it'll boil at a slightly higher temperature, which is actually why it helps in terms of cooking. It's not necessarily to make it faster per se, but it just raises the temperature of the water so that the cooking itself, the water is moving a bit more quickly, realistically, before it boils off. Another thing that happens is that freezing point becomes depressed, not that it's becoming sadder, but it gets lower. Okay, freezing point will go down. Vapor pressure is also lowered, which is also part of why the boiling point gets higher. That's related to that. And then osmotic pressure, but realistically that's more of a biology thing, so we're not going to worry too. Okay, But with boiling point elevation, like I said, it's related to the fact that the vapor pressure gets lower. Okay? The boiling point of a solution is going to be higher if something is dissolved inside of it. Okay? If you don't remember what vapor pressure is, remember, with vapor pressure, if you have a cup of water, part of the surface molecules, they are trying to get out. They would rather be gas molecules. They want to ascend to that level where they can just be free to do whatever they want. But that's difficult to do when you have all these other water molecules holding you back and bringing you back down. Okay? And so that push for some of the molecules to get out there is known as the vapor pressure. Right? That being said, the gas in the air, the oxygen and the nitrogen and all that stuff, they don't want any more people joining them. So they're pushing back down onto the liquid to prevent that from happening. So boiling tends to happen when the pressure of the water or the solvent pushing upwards, or liquid or whatever it is going up, is equal or greater than the pressure of the air around pushing back down. Okay? And so if you have a solution, it's not going to boil at the expected boiling point, say, for example, water, because there is still, there's something else in there affecting the movement of the particles itself. So the thing is that energy needs to be added to break a bond. And when you have something dissolved inside of it, chances are that, especially if it is something that's soluble, that has been dissolved inside, chances is, for example, water will have made an interaction and made a connection with that other solute that has been dissolved inside of it. Right? That means if you want that water to boil, not only do you have to overcome the forces of the water molecules who are attracted to each other and interacting and trying to hold them back, but there's also the solute that is doing the same thing. It's pulling it back down. They're interacting. Some of them have made a nice little relationship. They don't want the water to go. They want to stay together. And so it's very difficult for them to then break away from that. Okay? So, for example, if we have ammonia dissolved in water to make a solution, the boiling point ends up being 101.74. Not significantly higher, but that's just a little bit of ammonia. The more you put in, the higher that boiling point can go. In some places that you would see this happening is that in the car itself, you have something in there in your engine called coolant. Okay, the coolant is essentially a solution that has water plus some other chemical in there dissolved inside of it to raise the boiling point of it. Essentially, your engine gets hot when it's running. Okay, it's generating a lot of heat as it's generating the power to move the car, but you don't want the engine to overheat. And so you put this coolant inside to draw that heat out. Water itself would not make a very good coolant because its boiling point is 100, and it does do pretty well to absorb heat energy, but once it reaches that temperature, it's going to boil off. And that's not ideal because then you don't have any coolant left if it all boils away, and then the engine can overheat, and so that's bad. And so the thing that they put in does have water in it, but they've also dissolved another chemical called ethylene glycol inside of it to raise the boiling point of it so that more heat can be drawn out of the engine and for a longer period of time. Okay? And so keeps it cool from overheating as well. Okay? Though, just as a side note, what tends to happen though is that when the solvent does boil off, it does tend to leave the solute behind. Okay? So, for salt crystals, for example, to become a liquid, they have to be heated to over 1,000 degrees. And so they're going to get left behind. Eventually, the water, if you add enough energy, it'll break away from the bonds that it's made with the salt molecule particles. But it's kind of sad it leaves the salt behind. They had their fun. They were together for a bit, but it's moved on to bigger and better things. The salt stays behind in the lonely beaker, whatever it may be, pot, anything, pan, whatever it was. Okay. The other thing is freezing point depression. So again, similar to boiling point elevation, freezing point will become lower. And again, realistically, if you have water and it's starting to freeze, they're losing energy. They're becoming more compact. They're getting compressed. They're having a hard time overcome the intermolecular force. And so if more water is poured onto it, it's just going to bring it back and freeze it onto the existing ice. Okay. What happens though is that if you dissolve stuff in there, again, there's that disruption happening. The water molecules that would have formed the solid ice, they can't connect quite as well. There's something in the way. It's deterring it from becoming a solid. It's blocking its ability to bond and compact with the other water molecules. It's getting in its way. So to do that. So more and more energy has to be removed for this to happen. Okay. And so that it's basically forming a protective layer so that the water molecules can't all just coalesce together into that big compact solid anymore. So where you do see this happening is, as we live in Manitoba, or Winnipeg, winters get pretty cold. And so, the roads can get quite slippery. And what you may notice is that there's the trucks that go around putting salt and sand down on the roads. What that is doing is it's adding that salt layer to prevent the ice from forming. Okay. The thing is, if there are cars constantly driving on, that means there's a lot of friction along the roads. And that friction is actually a heat source which kind of melts the ice, preventing it from being too slippery. So that's why in the mornings, when you first drive, it ends up being the most slippery and the driving conditions aren't really great, or later at night. Because what's happening is that overnight, when there weren't so many cars driving over it, not only did it get colder, but there weren't any cars constantly running over that road to keep the friction up and warm it up and then keep the ice melted. Okay, so what the salt is doing while during the regular day where there's constant cars going off is that it's preventing that water the ice that's melted from re-solidifying back into the ice, because it's getting in the way from all of that water forming together into a compact solid ice surface. Okay, and so as long as cars keep going on that, warming up the road, that salt is going to prevent it from getting to a freezing temperature to get that slippery road. Okay, another thing, if you've ever flown in winter, you may have been delayed in the airport for half an hour, or whatever it may be, waiting to get de-iced. Okay, typically when they say they are de-icing the plane, what they're doing is they're spraying it with a chemical so that ice doesn't form on the plane itself. That would not be ideal. So they're spraying it with the chemical so that when it does go up and ascends into an area where it is colder and where there is higher chance of ice forming, that chemical prevents that from happening because it's coating it so that the ice can't even form to begin with. So that's basically it. I know it was a little bit long, but hopefully if you have questions, feel free to contact me and we can talk more about it. But that's kind of the big things within this 3 set of notes. Okay, so hope you are doing well and hope some of that made sense. Again, if you have questions, please ask, and see you later.